Okay, let's get started with our lecture. So we are going to continue talking about arithmetic for computers. Last time we met, we were talking about multiplication process, and the activity today is also based on multiplication. And then so today we'll start with a faster multiplier, get into division, and then majority of the time today we'll spend on is the two standards for IEEE 754, single precision format and the double precision format. The double precision format, 64-bit format, is the format that you use on your computers. It's universally accepted format. So we'll learn about how do you express numbers in those varying formats. So that's the second part of this lecture. All right. So before we begin with a faster multiplier, I want to ask you guys this question. Suppose you had this final version of your multiplier, right? This is what we did in the last class, where we tried to use one multiplier to multiply a 32-bit number with another 32-bit number to give us a 64-bit product result, right? That's what we did last time. Now, if you look at this final version of the hardware, can you guys tell me how many? So if the ALU was working on one operation plus per cycle, which essentially means I'm clocking my ALU, and at the active edge of the clock, my ALU produces one new result, right? How many such clock cycles would be required in order for me to completely get the result? 32, right? So I would need 32 cycles to get my 64-bit product result, which is a pretty long time. Now, what is the bad news here? The bad news is that if I went for 64-bit multiplication and higher bit multiplication, I'm going to linearly increase those cycles, number of cycles required, which is pretty bad in terms of speed. You guys agree with that? So that's the motivation for us to get into a faster multiplier. So what are we doing over here? Earlier, we had one ALU, which we were using 32 times. Now, what if we had the means to get 32 ALUs, but use them only once? The same way, right? Technically should work out the same way. One ALU being used 32 times versus 32 ALUs just being used once, right? So the goal is for us to get the answers quickly. So let's see what happens if I arrange my ALUs that are doing those additions to compute the partial products in this way. You can do that. How are you doing the multiplication? You're taking the least significant bit of the multiplier, ANDing it with the multiplicand, and that gets you the least significant bit of the product, right? So this is something like, if I go back here, taking the least significant bit of the multiplier, bitwise ANDing it with multiplicand to get the least significant bit of the product, right? And then you keep doing that. Keep moving left. Go back to my faster multiplier right here. So that's going to give you that. Next, you have the next most significant bit of the multiplier getting ANDed with multiplicand. This gives you 32 bits. This gives you 32 bits, but you only tap out one bit over there. These two 32-bit numbers get added, and then there is a pyramid going down, a trickle-down effect like that. So what is essentially happening? You have all your multiplier bits. You see this multiplier 0, multiplier 1, 2, 3, all the way to 31. So you have in green all your 32 bits of the multiplier. They are each getting ANDed with multiplicand, the entire multiplicand, to produce a 32-bit number. Those are being fed into adders. And once this pyramid, so here, how many adders do you have here? So let me highlight this level as, say, the green level or blue level. This is the blue level. Those are all operating at the same time, right? They are all happening in parallel. How many such adders are there at the blue level? This is going from multiplier 0 all the way to multiplier 31, right? So there are 32 bits. Each of these guys are getting 2 numbers. So there should be 16, yeah? 16 adders on the top level. Then those answers get fed into the next level, 2 at a time, right? So how many adders are going to be over here? 8. And then, of course, you will get 4, 2, and then finally you will get this guy 1, right? Pyramid down. So you see this 16 plus 8 plus 4 plus 2, you get what? 31 adders, right? Earlier we were using one adder 32 times. Now we are using 31 adders, but each of them is only being used once. How about the clock cycles? Oh, by the way, let me just let me just show you how the answer is being read. Least significant bit of the product here. Least significant bit of the answer of this adder becomes product 1, then product 2, then product 3, so on up till product 15. The final one adder will give you the 32 bits between position 47 to 16. And then you will get 48, 49, all the way up to 63. So those will be your 64-bit product result. Now let's come back to the levels. How many levels do you have? You have 16, 8, 4, 2, 1, right? So you've got 5 levels. So in terms of cycles, how many do you need? Earlier you wanted 32 cycles, right? Now you would need just 5 cycles to get the 64-bit result. Now, I will include one more thing. Can I do pipelining with this architecture? What that means is, suppose 2 numbers are getting multiplied and those 2 numbers are taking up this hardware. Like right now, they have gone in and they're using this part of the hardware. After one clock cycle, they have moved on and now they are using the second level. Can I bring in 2 new numbers for this? Can I bring in 2 new numbers to occupy? I just have to make sure that the product registers are different destinations. As long as I take care of that, I can use the same hardware. I don't even have to wait for 5 cycles to complete, right? Because it's in a hierarchy, in a one followed by the other form, I can use those 16 adders at the top for another multiplication problem as soon as it got used, right? So that's what we call pipelining, right? Trying to use the resources as much as possible all the time. Hold up, there was a question there. Go ahead. So this guy is coming from the least significant bit of this particular ANDing operation. This guy is coming from the least significant bit of this addition operation, and then all of them. So you get 1 bit each from all the others, but in the middle, the center, or this guy, right? At the very end, you get 1 adder, that'll give you 32 bits. The rest of the 30 bits, 16 from here, 16 from here. Go ahead. In maximum number of adders that you need, 6. Right. If I was using the same adders again. But this is sort of referring to, I already have 31 adders, and I'm going to use them, the same 31 adders for all the multiplication, but as soon as I get done with the first level, I will use the same level for another multiplication problem. A to B2, right? As long as I point the results to different destination registers for the product register, right? So that way, you see what is going to happen if I do that, all that in parallel. I don't even have to wait for 5 clock cycles, 1. 2, I'm getting a new answer every cycle, right? I'm getting a new product result every cycle. So that's increasing the speed by performing things in parallel and can be pipelined. Pipelined essentially means whenever I think about pipelining, I'm thinking about all those guys trying to put out the fire, right? A human chain trying to put out the fire, every guy is working all the time, right? Passing the buckets of water. So every guy working all the time, every level of adders in this case. Questions here? No? All right. Division. Now, it's going to be very similar to addition, multiplication, but it's going to be a successive subtraction instead of successive addition. We have four things over here. In the multiplication problem, we had multiplicand, multiplier, and a product register. Over here in division, we are going to have four things. In terms of results, we'll have a quotient and we'll have a remainder. In terms of operands, we'll have a divisor and we'll have a dividend. Now, when we think about division, you can think about it in terms of two approaches, generally two approaches. One is the long division approach, which you guys have learned in elementary school. It's going to take a lot of hardware to actually implement that. But there is another variation or another approach to division, which is the restoring division approach, which essentially does the same similar job, except it is going to require less hardware. Again, we are trying to subtract, and if our result becomes less than 0, we add it back, right? So we'll talk about how this works. Now, in our algorithms, we are going to have to check for 0, divide by 0 situations. So if there is a divide by 0 situation, then we are going to have either an exception handler program to run based on that, or make the answer not a number. And there are ways to identify what a not a number is. But we are going to need to check for 0 divisor. So that means this guy cannot be 0. Right? So let's talk about the long division approach first. In long division approach, what do you do? So suppose you're doing this, right? This is very much like your long division approach. You compare first your dividend with your divisor, right? You compare them. And if the divisor is greater than if your dividend is greater, in this case, dividend is much greater than your divisor, pretty big. What are you going to do in that case? You are going to write a 1 for the quotient and bring your divisor down here for a subtraction. Right? You're subtracting the divisor from the dividend if the divisor is smaller than the dividend, right? But you are going to need to compare, right? For that 1 to appear over here, you are going to need that divisor to be less than or equal to the dividend, which means I need a comparator. And we have all learned that a comparator is a lot more costly in terms of hardware than an adder or subtractor. You guys agree with that, right? Comparator is going to be more costly than an addition or subtraction. Next, if the divisor is smaller, which means that the divisor can be consumed, and the dividend is greater. You put a 1 in the quotient and then subtract. When you subtract, what do you get? You get a 1 here. When you get a 1 here, what do? You compare again. 1 is smaller, you bring down the next bit. When you bring down the next bit, what do? You put a 0 in the quotient. When the divisor is smaller, sorry, not the divisor. After you use the subtraction, if the dividend is smaller, you keep adding zeros to your quotient. You guys agree with that? Dividend is smaller than the divisor, put a 0. Dividend is smaller than the divisor, put a 0. So based on that comparison, if your dividend is smaller, you keep adding zeros to your quotient. Finally, when you bring down the last bit here, which can be accomplished by shifting operations, now you compare, you are going to see that the dividend is greater than your divisor, which means I can put a 1 there, Get your divisor here, subtract, and that will be your final answer. All the bits have been consumed. Bottom line is this. Depending on how the comparison goes, I will either put a 1 in the quotient or a 0 in the quotient, followed by bringing down the next bit. Now, so the problem over there is the use of the comparator and that being costly. So we can do the restoring division. Restoring division means I'm not going to spend time doing the comparison. I'm simply going to blindly subtract. I will keep subtracting. And if my answer of that subtraction is positive or negative, that will tell me how they compared, right? So if do the subtraction regardless of how they compare, and if the remainder is less than, if remainder goes to less than 0, the subtraction operation is negative, then add the divisor back. So you're retracing your steps if your answer, the remainder, is less than 0. Now, as far as sign division is concerned, it is going to work really similar to how we had sign multiplication. Do the division for the absolute values, take care of the results, the sign of the results separately. Next, we'll start with the flowchart, and then our goal will be to put it into a hardware form. So when you look at the flowchart, you start here. You're trying to do this for what? 32-bit divided by 32 bits. What is going to happen? Well, the first thing is what? This is the restoring division. So first thing is subtract. Straight away, subtract the divisor register from the remainder register. But why are we subtracting it from the remainder register? All right, before we do that, let's talk about the registers that are involved. So registers involved in this. For multiplication, we had what? Multiplicand, multiplier, and product, right? And at the very end, we figured out how to not have a 32-bit multiplier and combine it with the product register itself, right? So before we get to the optimized hardware, what are the registers involved here? We will have a divisor register. We will need that. You would think that we will need a dividend register, but there is a way to not have this. And then you will need a remainder register, and you will need a quotient register. So what I can do is, instead of initializing the remainder register to be all zeros, I can initialize the remainder register as the dividend itself. My remainder is the dividend. And then I can keep subtracting from that remainder register. You guys see that? So initialize, I don't need this anymore, because I'm going to initialize remainder register with dividend. So you see what we are doing here? We are saying, this is my dividend. I will initialize the remainder register to that value, and I will keep subtracting from that value. Eventually, I'll get whatever I get at the end in that same register, right? So I'm treating the remainder register as my dividend, and I'm keep subtracting from that. And based on that subtraction result, I either get a 1 or a 0 in the quotient register. All right, so I don't need the dividend register right now, right? Because I've initialized things in the remainder. I've put that number in the remainder register. I'm subtracting from there. Okay, so what am I subtracting from what? Subtract the divisor register from the remainder register. Now it makes sense. We were trying to subtract divisor from dividend. That value is in the remainder. So we subtract divisor register from the remainder register, and we are going to place that remainder result also back in the remainder register, while checking the sign of that result as well. Because depending on how that compares, after we do that subtraction, two things can happen. Remainder can be positive, 0 or greater than or equal to 0, or it can be less than 0. If it is greater than or equal to 0, that means that the divisor can go into the dividend. right? If it is less than 0, it means that no, you need to make it bigger. Get one more bit, put a 0 in the quotient, and so on. So that's what we do here. If it is greater than or equal to 0, we are going to shift the quotient register to the left. And when you move the quotient register to the left, it will create an empty spot, right? Put a 1 in there. That's how you put a 1 in the quotient. Move left, put 1. Move left, put 1. Or if it was the other case, less than 0, move left, put 0. Move left, put 0. And as you're moving left, what is happening? You're dropping the bits of the quotient register, right? The most significant bits. They keep dropping. Whatever those, if you initialize it to all zeros, those zeros will keep dropping, and your new answer for 32-bit quotient will be keep coming in as ones and zeros. All right, so that was when it was greater than or equal to 0. If it is less than 0, what do? You restore, hence the name, restore division. So restore the original by adding back your divisor to the remainder register. So sort of undo step number 1, right? After you do that, you also need to do the shifting of the quotient register to left, and then the new significant bit is 0. So you are going to, after you compare, you are going to move the quotient register to the left. In any case, the new bit that you place, the rightmost bit, is either going to be a 1 or a 0. It is going to be a 1 if it was greater than or equal to 0. It is going to be a 0 if it was less than 0. What is going to happen after 33 cycles of, 33 repetitions of this loop? You are going to get rid of all the zeros in the quotient register that you initialized with, and then you are going to get that 32-bit result in your quotient register, filled with bunch of ones and zeros, depending on how these comparisons went. What happens to your remainder register? Well, at the very end, whatever is in the remainder register, that is your remainder register. No need of a dividend register. Divisor register will stay as the divisor register. That operand stays as is. Now, I need to also move the divisor register to the right by 1, because if I move to the right by 1, to take care of this subtraction followed by this subtraction followed by this subtraction, I'm moving that as well. Right, so that is going to be taken care of at the very end. Shift divisor register right by 1. Keep doing this 33 times, and then you're done after that. And your results will be in the quotient register and your remainder register. So that's one way of doing things. And if you think about it in terms of hardware, that's what you will have. You will have registers for quotient 32 bits, divisor 64 bits. Why is the divisor 64 bits? Well, I'm using the left half of the divisor register as the divisor, and I'm putting all zeros over here, and I'm going to keep moving to the right. For the quotient, where am I moving? I'm moving left for the quotient, and every least significant bit is going to be filled with either a 0 or a 1, right? So I can highlight this and say the rightmost bit is a 1 or a 0, depending on that comparison. Where is the dividend? Dividend is over here, initially dividend, right? So remainder is initially dividend. If you have a 32-bit dividend, then you have a bunch of zeros followed by the 32 bits for the dividend over there. I need to occupy 64 bits over there. Why? Because I have a 64-bit ALU. Why? Because I have this number as 64 bits. So what is going to happen? This is your control block, control test. What is it looking at? It is looking at the answer. The only thing that this guy is looking at is the answer not the answer, the sign of the remainder, right? So whatever resulted after that subtraction operation went into the remainder register. You are looking at the sign of that remainder register. Greater than or equal to 0, less than 0. Depending on that, it is going to send all these signals. 1, I have performed the subtraction, write it on top of the remainder. whatever you subtracted, divisor, remainder equals remainder minus divisor, right? You're putting it back into the remainder. When to do that subtraction? Shift right by one place. Shift left by one place and put a new 1 or a 0 at the very right. Right? So all of those are going to be sent by the control test depending on the sign of the remainder. Now, a few things that are a problem. 64 bits. Can we think about doing this with 32? 64-bit ALU. Can we do it with 32-bit ALU? Another quotient register. Can we maybe skip the usage of a quotient register just as we skipped the use of a multiplier? So all of that can be accomplished with an optimized divider. So optimized divider, what do we have here? We have remainder, which is 64 bits. The right half of the remainder is where your quotient goes, and the left half of the remainder is where your dividend is. So 32 here, 32 there. 32-bit ALU, 32-bit divisor, just as we had before. Now, you are not shifting right for the divisor. You are doing all the shift operations to the remainder register itself, whether it is shift right or shift left, or whether to update the result. All right, so that's it. And so the control is still doing the same thing, looking at the sign of the result, and depending on the sign of the result, it is going to either put a 0 in the least significant position of the quotient here, or put a 1 if the remainder was greater than or equal to 0. All right. So this sort of brings it down to the same hardware that we used for the multiplier, right? So it's very similar looking. It looks very similar to the optimized multiplier we had. We just called those registers by different names, right? Instead of divisor, we called it multiplicand. Instead of remainder, we called it a product register. That was it. We still were using 32-bit ALU. Over there, we were doing addition. Now we are doing subtraction. So what that means is we can use the same hardware to do multiplication and division. We are just going to treat those registers differently for different purposes. All right. So this completes your division. How do you do division in terms of hardware? Our activity focuses on multiplier. That's a little bit more straightforward. You guys can do that after the end of class. Now we are going to move to your next lecture, which is the IEEE single precision format and double precision format. So why do we need it? How are you going to express numbers in it? What is going to be the range? What is the precision? We'll talk about all those ideas. Representing real numbers. Now, we need a consistent way to represent numbers. What do those include? They include fractions. They include very small numbers, 10 to the negative, whatever, 14, 15 here, or very large numbers, because that is going to be a practical need in, say, computer graphics or any kind of scientific or engineering computation. You will have the need for expressing very, very small numbers to very, very large numbers. Includes fractions, includes signed numbers, and so on. Recall the scientific notation, and this is in the decimal world, right? So this is not in the binary world just yet. This is in the decimal world. How do you represent any number in the scientific notation? Your number is -1 raised to sign, so that takes care of whether the number is positive or negative. Then you will have significand multiplied by 10 raised to exponent. For example, if you had, say, 4564.25, then you would write it as 4.56425 times 10 to the 3. So 4.56425 would become your significand, and 10 to the 3 would become your exponent. Now, significand, when we move to the binary world, we are going to refer to significand as either mantissa or fraction. And there is a difference between significand and fraction. And we'll explore that. So for significand, there's a rule. The rule is exactly one non-zero digit to the left of the decimal point. So you see this? Exactly one non-zero digit to the left of the decimal point. That rule has to be met for it to be qualified as a significand and for you to be able to represent that in scientific notation. But for fraction, there are two things in significant, right? One is the integer part, which is the 4 here, and then there is the fraction part, which is the 56425. So when you are in the decimal world, what can this be? Integer part, what can that be? Can it be 0? No, it can be 0. It can be 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah? Those are your 9 options for this guy, right? How about binary? If this conversation was regarding binary, what would be the value of your integer part? 0 or 1? Can it be 0? It has to be a 1, right? It has to be a 1. Why? Let me ask you guys this. Can you give me any unsigned number? Think of any unsigned number. 9, 15, 305, whatever number you want. What is the most significant bit? Unsigned, right? If I say unsigned, I'm not keeping any limitation on the number of bits, right? Think about it. 1, 1, 2, 1, 0, 3, 1, 1, 10, 1, 0, 1, 0, whatever, 31, 1, 1, 1, 1, 1. The most significant bit is always 1, right? And this continues. No matter how far you go, I'm not including 0 here, because for 0 I have a plan, for infinity I have a plan, but for all the numbers that are in the middle, their most significant bit is going to be always a 1. Now earlier, there was some information. I had to say 1, 2, 3, 4. In the decimal world, I had to say that because it could be one of those 9 options. Now do I have to say it? No. I can keep that 1 implicit. I say 1 bit, right? Because it's always going to be a 1, no matter what. You guys see that? So I don't need to explicitly mention that 1. So for binary numbers, you will have significand as 1 dot whatever, mantissa or fraction. So I only talk about the fraction. I don't talk about the 1. But when I'm converting numbers, I'm going to include that information because I know it. You guys see that? All right, let's go back. Okay, so significand is going to be related to mantissa or fraction. So some books call it mantissa, some books call it fraction. We will call it fraction. And then, of course, you will have exponent here. There are 3 components to representing the number: sign, exponent, and significand. Now, you guys are all smart guys. When I say guys, I'm also including the girls, by the way. How many bits do you need for sign? Bits. So when you think about it binary, how many bits do you think you would need for sign? 1, right? Just 1 bit you would need for sign. 0, positive, 1, negative, done, right? How many bits do you think you will need for exponent? How many bits? Because this is a standard, right? So we have got to put it as a standard for everybody to follow. We cannot sort of be flexible about it. We're going to have to put it as a rule down for everybody, every computer to follow. How many for exponent? How many for the fraction or significand? We're going to have to go ahead. Well, 32 would be for the entire one, right? So 32 or 64 would be for the entire combination, the 3 components combined. So now think about this. The reason why we need to make a standard is because 10 people over here, 10 people online, combined, 20 different options could have been there, right? Everybody could have come up with their own, I want 10 bits in my exponent. I want 5 bits for my exponent. My application is flexible, right? So everybody could have come up with their own strategy for the division of bits between exponent and significant. Sign, okay, everybody agrees 1 bit, but exponent and significant, how do you break it up? Because actually, exponent is related to the range of the numbers and significant is related to the precision of the numbers. So depending on what your application requires, bigger range or higher precision, you would want more bits compared to the in more bits in the exponent versus significant, right? So end result, divergence of standards, right? Everybody has their own desire. Bring everybody to the same page. Why? Because things should be portable, right? So whatever I do, whatever work I do on one computer should be portable, right? All those scientific calculations should be portable. So everybody has to agree. So that's why we talk about the standards. All right, so let's come back. So I've given you almost all the motivation of the lecture. We'll again talk about these things. Let's come back to this. So 3 components, we talk about these 3: sign, exponent, and significant. For example, this number can be expressed in this, in the scientific notation. I've got it to be normalized, right? This is called a normalized significant. Why is this normalized? Because I see at exactly one non-zero number to the left of the decimal point. That's called a normal or a normalized significant. Times 10 to the 3. So my exponent is 3. So if I write those numbers down, I've got sign as 0, I've got exponent as 3, and then I've got my significant as this number here. So a couple of things. Significant always has exactly one non-zero digit to the left, and it is called normalized significant. So that's called a normalization. If they are normals, they are also denormals. So denormals are numbers that are really, really, really small, in which the most significant bit cannot be a 1. We'll talk more about that as well. Next, range. So let's try to take a look at the impact of having more bits in one field versus the other. So let us, and again, we are still in the decimal world here. Suppose we have 2 digits for exponent, so negative 99 to positive 99, and we have 2 digits for significant. So it can go from 0.1 all the way up to 9.9. If that is the case, what would be the range of numbers you can represent? Well, the smallest would be what? The smallest would be negative 9.9 times 10 to the positive 99, right? That would be the smallest number you can represent with 2 digits, those 2 digits in exponent and 2 digits in the significant. You guys agree with that? Next, how do you go for the maximum? Well, it's going to be 9.9 times 10 to the 99. The difference between the max and the min is going to tell you the range, right? So that's your range number. What if I wanted a bigger range? Well, you would put more digits in the exponent to increase the range. More digits in the significant wouldn't help you, right? If you had 0.01 all the way up to 9.99, that would not help you with the range. If you wanted to increase the range, you increase this, right? 10 to the 99, 10 to the 999. That would be a big jump in the range. So the range of numbers you can represent is directly connected to the exponent field. Can I say that? Exponent field and range, they have a relationship. Questions? No? How about the precision? So range is from what to what can you represent? Precision is what are the jumps, right? How close is the next number? Let's analyze that again with the same 2 digits for exponent, 2 digits for significant. So negative 99 to 99 for exponent, and 0.1 all the way up to 9.9 for significant. If that is the case, think about the precision very close to 0, and we are looking at only the positive side of the real line here. When numbers are very close to 0, what is going to be the precision? The one value between the difference between two adjacent values. It is going to be the smallest jump you can make in significant times 10 to the negative 99, right? But as you are going up in the positive line, what is going to happen to your exponent? It is going to increase. And as it increases, you see what is going to happen far away. Here, the difference between two adjacent values is going to be 0.1 times 10 to the negative plus 99. What that means is, as you are going right on the positive real line, your precision is changing. It's continuously varying, right? So you're able to have very, very precise values close to 0, but as you go up, you're going to have that precision go down. Varying precision. But how do you change this? How do you have a better precision? Well, you can increase the precision by increasing the digits in your significant. So instead of having 0.1 to 9.9, you can have that as what? 0.01 to 9.99. In that case, what would happen? This would be 0.01 and this would be 0.01, right? So that would be a better precision case compared to the one before. You guys see that? So significant connected to precision. Now, applications sometimes require a lot bigger range, and applications may sometimes require higher precision. So depending on that, you would sort of adjust the bits, right? The bits, number of bits in the exponent field versus the significant field. Now, here is the thing. If you were to decide one, what would you look for? You would look for a division between those number of bits in such a way that almost all the applications are covered, right? The range is good and the precision is good. If you are able to get that balance, that's what you will make into a standard. There are a few other things we need to talk about before we get to the standard. The concept of overflow and underflow. Whenever you have numbers that you have, say, successfully represented in scientific notation, what do you do with numbers? You do arithmetic with numbers. The result of the arithmetic, what happens to that? Can be correct or can be incorrect. Because now what do you have? You have a limitation on the number of digits that you are using for exponent and significant. The moment you put a restriction on the number of digits or the number of bits, what do you end up with? You will end up with a possibility of overflow, underflow. So for example, if you do some addition or subtraction, some arithmetic operation, if your answer falls within this range, right, that range, the minimum number you can represent on the positive side and the maximum number you can represent on the positive side. If your answer fits in that range, that's the safe zone, which means no overflow. However, if your answer goes here, then you call it positive underflow, positive overflow. More than the maximum number you can represent, positive overflow. Positive underflow is smaller than the smallest number you can represent, because you cannot represent that, right? That's for positive numbers. That's the result of the arithmetic. Next, you can also have negative underflow and negative overflow. So whenever in COCO, when we talked about overflow, it was very general, right? So we said overflow, what does that mean? It includes, it didn't include underflow. It essentially included positive overflow and negative overflow. But here we are trying to be a little bit more specific in our terminology. So again, the same scenario. The maximum number you can represent with those 2 digits for exponent, 2 digits for significant on the negative side, and the minimum number you can represent. If answer falls in this range, you're safe. If answer falls here, you have underflow, negative underflow, or negative overflow. This is the, why is this not the numbers? Why is this for the answer? Like you have operands and then you have results. Why am I saying that this is going to apply for the results and not the operands? Good. Right. So the operands are going to be limited anyway, right? So the ISA or the space given for the numbers is going to be 32 bits or 64 bits. So there's no possibility for you to sort of change that. You cannot go for 33. However, what you do with those numbers, that you cannot control. If you're trying to add, then that is sort of out of your control, where the result goes. All right. So now let's come to the scientific notation for binary numbers. And I'm calling this floating point. Why am I calling this floating point? And what is the opposite of floating point? What is the opposite of floating point notation? Was it? Integer. No. So it's about the point, right? So floating point, if it was not floating, it would be fixed. So fixed point notation, floating point notation. What is the difference? Well, in fixed point notation, the decimal point or the binary point, if we are talking about decimal numbers versus binary numbers, is fixed. 1.2, 300.56. These are fixed. What is floating? 3.154 times 10 to the 2, 10 to the 3, 10 to the 4. By adjusting the exponent, I'm keeping that point floating, right? Same number, but using that exponent field, I'm able to move it left or right. Keep it floating. You guys see that? Now, when we were talking about things in the decimal world, what did we have? We had this guy as 10. So the only thing really that changes is, instead of 10 raised to exponent, now you're going to have 2 raised to exponent in terms of the scientific notation. So you have got -1 raised to sign for positive or negative numbers, followed by the significand. And we already talked about the fact that if you are going to be in the binary world, then significant has the most significant bit as 1, which is going to be redundant for majority of the numbers. Then you have 2 raised to exponent. Now, what are your fields? You have 1 bit for sign. Everybody agrees. We are not able to agree upon the number of bits used for exponents. And we know that exponent is going to control what? The range of numbers you can represent. And then we are not able to agree upon the number of bits used for the significand. Whatever remains, of course, 32 minus that or 64 minus that. But we are not able to agree on that, right? All that we know is this guy controls range, this guy controls precision. Let's see. Okay. That's why we need a standard. Floating point standard developed by IEEE in 1985. This was agreed upon in 1985, so a long time ago. And since then, we have all been following that. Till date, all our digital devices use the same 64-bit standard, 64-bit floating point standard. Developed in response to divergence of representations, like we talked about. There are 10 people here, 10 people online. If I said, all right, you guys design your own 64-bit format, 64, I'm giving you 64 slots. Decide how many bits you want for sign, how many bits you want for exponent, how many bits you want for fraction. You guys are all going to be in disagreement, right? Divergence of representations. So in order for us to be able to port scientific code, we are going to need to agree to a standard, which is what this is. There are 2 representations that are universally adopted. One, which is simpler, and we'll talk about that in a lot of detail, is the 32-bit single precision format. And then, of course, we were not happy with the range and precision we were getting with that, so we went for 64-bit. So 64-bit is going to be our double precision format. In the IEEE, and now it is decided, right? So now there's no longer this confusion. It's decided. 8 bits for exponent and 23 bits for fraction. In reality, I have 24 bits, but I'm only writing 23 bits, right? Because I know that one of the bits is 1. We talked about that. All right, so let's see, sign 1 bit. Everybody is okay with that? Yeah? Positive, negative, I need 1 bit for that. Let's put that all the way up front, the most significant bit of that 32-bit sequence. Then you have 8 bits for exponent field. Exponent controls the range of the numbers. You are telling me that 8 bits corresponds to a range of 10 to the negative 38 to 10 to the positive 38. Where is this coming from? That's a very important question. Let's go into it. With 8 bits, what is the smallest sequence and what is the largest sequence with 8 bits? Can I say that? With 8 bits, I can start at 0, all zeros, and end at all ones, right? So if I look at it in terms of unsigned numbers, this guy is what? 0, and this guy is what? 255. Yeah? Now remember, I need one sequence for actual 0, and I need one sequence for infinity. Yeah? So the thing that is used for actual 0, if I use that, and I use for this guy for actual infinity, all the other numbers, finite numbers other than 0, are in the middle, right? So in the middle, how much do you have? You have 1 to 254, right? Because you have reserved the 0 guy for 0, actual 0, and you have reserved the highest number for infinity. You have 1 to 254. Now 1 to 254 is what? These are all positive exponents, right? 2 raised to 10, 2 raised to 20, all the way up to 2 raised to 254. Well, you don't want all of them to be positive exponents. You may want negative exponents also, right? So if you want positive as well as negative, you split it in the middle. When you split it in the middle, you can have 127 on the negative side, 127 on the positive side. So that will give you the range of 2 raised to negative 126 to 2 raised to 127. That would be the range of numbers you can represent with 8 bits in the exponent field. So I've told you why smallest, largest, 0 to 55. Assign this to 0, assign this to infinity. You're left with 1 to 254. That's 254 numbers. Sometimes I need positive exponents, sometimes I need negative. I'm going to split that in half. 2 raised to negative 126 to positive 2 raised to 127. That would be the range. When you convert this to decimal, what do you get? A power of 2, when you actually convert it to power of 10, it will approximate to that range, 10 raised to negative 38 to 10 raised to positive 38. So you would think that it is pretty good, right? Like it's sort of 10 raised to negative 38 to 10 raised to 40. That's a pretty good range, right? And with 23 bits, actually with 24 bits, you are getting about 6 decimal digits of precision. So that's also pretty decent. But there is still an opportunity to have a bigger range and a better precision, which is 64 bits. When you actually go to 64 bits, the jump over here is pretty significant. You go from 10 raised to 38 to 10 raised to 308. Right? So you can go really, really, really small and large numbers. All right, so we talked about that. Okay, I think this is it. Questions here? Now, what will be our goal? Our goal will be, you give me a number, and I'll tell you the 32-bit sequence. Or 32-bit sequence, I'll tell you what that number is. Right? So to do conversions between decimal numbers and the standards. So let's talk about the 32-bit format a little bit more. And some of these things we have already touched upon, the most significant bit being 1 already. But I need to tell you guys what is easy here and what is difficult here. The easy part is sign. The next easy part is the fraction. The confusing part is the exponent, because exponent actually is not represented as is. Exponent is actually represented in excess 127 format, expressed in excess 127 format. What that means is the exponent over here equals true exponent plus 127. So whatever you want to represent using those 8 bits is the true exponent, the actual exponent of the number, the true exponent, plus 127. When you put that as plus 127, what are you doing? You're taking even the negative true exponents and putting it onto the positive side. You guys see that? So if you have a number, say negative 10, right, in the exponent field, so you have something like 2 raised to negative 10, right? So if you have 2 raised to negative 10, your true exponent is negative 10. But can you represent negative 10 in exponent field? No, you can't, because we are not talking about it as signed and unsigned representation. We are only talking about it as unsigned. So what are we going to do? We are going to push things onto the positive side. How can we do that? We can add 127 to it. Right? So when you add 120, because it can go as small as negative 126, right? So if it goes as small as negative 126, you can still put 127 over it to get it onto the positive side. You can see that? So negative 10 would be the true exponent, plus 127, you get 117. 117 would be the exponent, and when you convert 117 to a 8-bit sequence, that will be your exponent field. You guys see that? Now here is a question. My exponent field is 7 bits. Exponent field is 7 bits. It should be in what format? Huh? If I had 8 bits, then it was in the excess 127 format. If it was 7 bits, it would be in x63 format, right? So that means, again, we'll do the same thing. Exponent equals 2 exponent plus 63 for that case. Again, our goal is the same, right? Whatever it is, you have to push it to the positive side. Now here, what is the number for 11? And there is a reason why I'm talking about 11. So I talked about this. What if this exponent field was 11? Excess what? Format. Was that? 1023. Why did I talk about this special case? Because when you go to 64 bits, your exponent will be 11 bits, and it will be in the excess 1023 format. And now you know why. Okay, let's see. So you've got, let's get into the other things here. Why did significant change to a fraction, right? So you see this, we changed it to a fraction. Significant was what? Integer, point, decimal or binary, fraction. I don't need that 4 now. Why? Because now it's binary, and when you are talking about binary, that is going to be 1. So it is going to be 1 dot, this is not dot, this is a binary point, followed by all the bits that go in the fraction, right? Significant is integer dot fraction. My integer is always going to be a 1. So why represent it? I can just represent the fraction. That's the reason why I have the fraction bits here, 23 of them. Next, binary. Oh yeah, we talked about that. Binary is special. The one non-zero bit to the left is must be a 1. So the form is going to be what? The form is going to be 1 dot all the bits that are in the fraction represented in 2 binary form multiplied by 2 raised to exponent, right? So all the exponent field is represented as y's, all the fraction bits are represented as x's. They are going to be different. We just want to identify them, so we are putting the same x. And then fraction is just the bits over here. So whatever those are, you put it over there, right? Go ahead, Alma. 2's complement form for exponent, we could. But if I just adjust that to be in a different format, then I don't have to worry about that conversion between positive and negative numbers. I don't have to treat, so you could. But in the standard, back when they designed the standard, they said, all right, let's just treat that as unsigned field. I will just adjust the excess number, excess blank number. All right, let's see. Fraction. Okay, so 1 plus fraction is your significand, while your fraction is between 0 and 1. Right? We are going to have 1 point, whatever number. That number is going to be between 0 and 1. 0.5 is between 0 and 1. All right, let's move on here to normals. What do normals mean? Normals mean 1 dot whatever. Right? So normals have the most significant bit to the left of the binary point as 1. After the binary point, you have all the fraction bits. So if you see a 1 there, to the left of the binary point, you know it's a normal. Oh, sorry. You know it's a normal. Leading one of the significand is implicit. Why? Don't need to write that 1 because I already know it has to be a 1. So for example, if you look at half, you write half not in this way, but you write it in this way. You see what is the difference? Over here, you're saying 0.5. When I convert it into decimal, it will be 0.5 times 2 raised to 0. But I want it to be normalized. So if I want it to be normalized, I'm going to move the binary point left by 1 place, and I'm going to put it 2 raised to negative 1. Now, you guys are very comfortable with moving the decimal point left and right? To adjust the exponent, 10 raised to 2. You want to consume the 10 raised to 2, move the decimal point right by 2 places. Yeah? Now we are in the binary world. So what is it that going to translate to? You want to move the binary point left and right. It is going to be the same number of places, whatever is 2 raised to 5. If it is 2 raised to 5, if you want to consume that 2 raised to 5, you need to move the binary point to the 5 places right. You guys see that? So over here, if you want this number to be normalized, you want this binary point to move 1 place to the right. Yeah? If you want this binary point move 1 place to the right, you are going to have to put this as 2 raised to negative 1. So when you consume this 2 raised to negative 1, this guy moves back over here, and you get your half. Good. Zero is going to be a special case, all zeros. So if the 32 bits are all zeros, that is 0. No. So we have 32 bits, right? So I can have a 32-bit sequence. So I'm going to have some identifiers. If exponent field is all zeros and fraction field is all zeros, that is going to indicate 0. If exponent field is all zeros and fraction field is non-zero, then it is going to indicate a denormalized number. So there's a table at the end where we talk about each of these categories. So we need an identifier for infinity, not a number, 0, normals, which we are talking about, and denormals. All right. So we talked about that. Only the fraction is included in the IEEE form. We talked about this. Exponent is represented in XS127 format. So whatever you have in the exponent field is actually the true exponent plus 127. We now know why 127 is chosen, but with some examples, it'll be very clear. So the value of your number in decimal is going to be -1 raised to sign, so that consumes your sign bit, followed by 1 plus fraction, right? Fraction is there, add 1 to it, you get the significant. 2 raised to exponent minus 127. What goes here? True exponent goes here. True exponent is going to be what? Exponent minus 127. So that goes over there. Some examples? Writing out a 32-bit sequence can be time consuming, tedious. So instead, we are going to use hex representation to keep it compact. So what we have here is a number f that is being represented in 32-bit single precision format in hex. So you have got in hex C2E48000. So once you expand each hex digit as 4 bits, you will get a 32-bit sequence. Over here, the 32-bit sequence is this. And you see, there are going to be many cases when you guys are working on numbers where you will have sort of a run of zeros. You can just represent that using dots. 0, 0, dot, 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 0, 0, run of zeros. Now, once you have the 32-bit number, you can start isolating 1, 8, 23. Sign, right? Negative. Good. Sign is 1, negative number. We have got this negative piece over here now. Easy. Next. This is what? This is the exponent field. Is this the true exponent? No. That is the exponent field. So I want true exponent, right? So I'm going to take the exponent field, convert that to decimal. Whatever value I get, I'm going to subtract 127 from it to get my true exponent. So when I do that, all these zeros, 101 corresponds to 133. So my true exponent, I should write true exponent here. True exponent is going to be 133 minus 127 gives you 6. Yeah? So I've got the exponent here, I've got the sign here. Next, how do I get significant? I get 1 dot fraction. So 1 dot is no problem. I get that because it was hidden, right? 1 dot is there. All the others go here. All of this goes here. You guys see that? 23 bits of the fraction there. Now, in order to find the value, what am I going to do? Negative for the sign, 1 dot for the significant, 23 bits of the fraction multiplied by 2 raised to true exponent. So there are a couple of ways to do this. What you can do is you can convert this guy from binary to decimal and then multiply it with 64, right? That's one way of doing it. Another way of doing it is, let's try to consume this 2 raised to 6. How can you consume this 2 raised to 6? Just move this guy. 1, 2, 3, 4, 5, 6, right here. Yeah. So you're going to get that number, convert it into decimal, you get negative 114.25. So you can use a decimal to binary conversion using a calculator to do that conversion quickly. All right, questions here? No questions? Very straightforward, easy peasy. Excellent. I think we are ready for an example then after squared paper. All right, let's go the other way. Let's go the other way with, I will give you the decimal number and try to tell me the 32-bit sequence. And the decimal number we'll take is interesting. Let's take negative 12 point. I need to be careful with these guys. 3125 will do it. 3125 will be nice. All right, I'm trying to get a number off the top of my head. 3125. How can I make 3125? 0.25 plus 0.0625. So there should be a way to get it, right? All right, let's see if I can do this. Maybe we'll have to change the number, but I'm trying to take this. Negative 12.3125 in decimal. I want to convert this to IEEE 754 single precision format. So I need to give it 32 bits, maybe in binary or in hex. We'll get it to binary, and I am sure you guys can do it on hex. So let's start with that, and let's work it. 12. What is the 12? 12 in binary is 1100, right? Yeah, done with 12. Now I need some help with this. I need what? I need 25, and I also need 625 will do it. Okay. So what is this going to be? 0 here, 1 here for the quarter, and I don't have anything after that, and I have 1 after that. Somebody has a calculator, please check. Please check this calculation. 2 raised to negative 2 plus 2 raised to negative 4 equals 0.3125. Question mark. Is it correct or not? Laptop. Oh, what? Calculator is not here. All right. If somebody gives a cal, is good. Okay. It's correct. All right. So I need to erase this. All right. So I've got 12. I've got 0.3125. Next. What is my number now? Sign I know. Let us look at the number. What is the number? It is 12.3125, right? If it is 12.3125, that is now being represented as what? 1100 binary point 0101 and then a run of zeros, right? You guys okay with that? Now, you see this? Is it in the normalized form? No, I need to normalize it. If I want to normalize this, I need to move the binary point to the left by 3 places. If I want to move that by left by 3 places, what do you get? You get 1 dot 1000101 multiplied by 2 raised to what? Positive 3, right? Because if I want to consume that, then I move places back. Yeah? So I got my true exponent as 3, which implies my exponent field is going to be what? 130. 130 is going to be what? 128 plus 2, right? So 128 is right here, and then plus 2. This is that, and then that. I think that's 130. Is it 130? 2 raised to, all right, I think it's 130. All right, you guys can correct me if I'm wrong there, but I did 128 plus 2. I got the 2 fine, and I get the 128 with. All right, so let's see. I think this is it, right? Like I'm ready for the answer here. Sign bit is 1, followed by the exponents, and then followed by the fraction. Fraction is just going to be this, right? This guy is 1 bit, this guy is 8 bits, this guy is 23 bits. That is how you represent negative 12.3125 in IEEE 32-bit format. Questions about this example? Oh, so I got, so I just worked in the inverse powers of 2, right? So this is half, this is quarter, this is divided by 2 of. So I knew a quarter is there because it's very close to a quarter. I needed something on top of that. So I was trying to choose a number which sort of meets that criteria. Sometimes it can, I can miss and then it'll go on forever and I'm like, it's not ending. So I wanted to choose a nice number. So yeah, 0.25, and then if I divide it by 2, I get 0.125, and then I divide by 2, I get 0.0625. What's up, Jennings? The exponent field. Okay, so exponent field. So you see this, once I got this, are you okay with this number here? You're okay with this? The one, okay, so once I had that, if I want to normalize it, then I need to move the decimal, sorry, not the decimal, binary point to this location here, right? So if I want to move the binary point to this location here, then that would be 3 places to the left. And I can do that if I include this, right? So I've got one binary point, all of these numbers, followed by 10 to 10 multiplied by 2 raised to 3. Yeah. So once I get this is my true exponent. True exponent is 3, and my exponent field is in excess 127 format. So if my exponent field is in the excess 127 format, my true exponent is 3. So what's that? They add together. That's right. 127 plus 3. So I get 130 for the exponent field. True plus 127. True is 3, 127 from the excess 127 format. So I get 130, convert it into 8-bit unsigned value, which is 100, whatever that 8-bit sequence is, and that will give you your exponent field right there. Next question. Denormals or subnormals. What are they? They are going to be for numbers that are very, very, very close to 0. Remember our range with 32 bits? It was 10 raised to negative 1, sorry, it was 10 raised to negative 38 approximately to 10 raised to positive 38, right? What if my number is smaller than this? If my number is smaller than 10 raised to negative 38, I should have a way to represent that. Because you see, there was one bit that was sort of implicit, right? That 1. So if I use that 1 position, I may be able to represent even smaller number than 10 raised to negative 38. So that is going to be my denormalized numbers, used for tiny numbers around 0. So it could be positive, negative, depending on the sign of the number. The significand is not normalized. In this case, you see you have a 0 followed by all your bits. Earlier, you had 1 dot followed by the bits. Now you have 0 dot followed by the bits, multiplied with 2 raised to 0. In this case, significand is between 0 and 1. Fraction is between 0 and 1. Significand is fraction. So instead of having that 1 dot fraction, I have 0 dot fraction, because it's a very, very small number. True exponent is no longer in excess 127. It is actually in excess 126 format because of that 2 raised to 0. So whatever you have in the exponent field, subtract 126 from it, and you get your true exponent. So if you put these things in the value of the number, you have negative 1 raised to sign as before, multiplied by the significand or the fraction, multiplied by 2 raised to negative 126. So you've got 8 bits for the exponent, 23 bits for the significand or fraction, and then 1 bit for the sign. Used for tiny numbers. Let's do an example to see how it's going to work out. So at the top here, what do you have? You are given the number in 32-bit format. The first thing that I'm going to need to identify is whether it is in the normalized or the denormal representation. And I can do that when I look at the exponent field and the fraction field. What is my exponent field? All zeros. What is my fraction? Non-zero. If your exponent field is all zeros and your fraction field is non-zero, that is an indication of a denormal or subnormal number. It is captured in this particular table right here. For denormals, could be a positive, could be a negative number. So you can have a very, very tiny number around 0. It's not only just for positive, also for negative. The exponent field has to be a 0. And for fraction, you can have any non-zero, any non-zero value. So at least 1 bit has to be a 1. So I see that. So that is going to tell you whether it's a denormal or not. Normals were here, right? Normals where sign could be a 0 or a 1. Exponent field starts at 1, ends at 254. We talked about that. And then any bit pattern going over there. So that is for the normals. And then I think we also talked about this. 0 could be positive, could be negative. Exponent field is all 0. Fraction field is all zeros. And if you see all the bits are 0 except for the sign bit, you know it's a 0. Right? So we have sort of done these. We'll do the others later. Let's come back. Where are we? We are here. So we are given this 32-bit sequence in hex representation. You expand it, write it out as a 32-bit sequence. Once you write it out as a 32-bit sequence, then you can see the exponent field, all zeros. Fraction field, non-zero. You know it's a denormal right away, right? Now, if you know it's a denormal and it's a negative number, so you've sort of gone here, right? Significand is non-zero, means that our normal is not normal. We are dealing with what denormal? Negative for what? This guy. 0 point, whatever bits you have for the fraction. What do you have for the fraction? You have all of these guys for the fraction. That goes right there. Multiplied by 2 raised to negative 126. True exponent is 0. Exponent field is in excess 126 format. So you get 2 raised to negative 126 over here. Whatever this evaluates to, that would be the number. It will definitely be less than 10 to the negative 38 or less than 2 raised to negative 126. Convert 9 to IEEE 754. What is that going to be? Is this going to be a normal or denormal? It's going to be a normal, right? So 9 is not close to 0. It's pretty far away. So how do you do this? 9. Represent it in binary 1001. Normalize it 1.001. times 2 raised to 3. You got the true exponent in 3. You have got the fraction bits over here, 0, 0, 1, followed by zeros. So exponent 3 plus 127, you've got 130. That's your exponent field. 0 for the sign, 8 bits for the exponent, and then all of these fraction bits go over here, giving you the value in 32 bits. So this is a simpler example than we did. We actually looked at a negative 6.75. So we had a fraction part as well. This is just an integer part. Questions about this example, converting 9 to 32-bit format? You just need to remember to do the normalization. Once you do the normalization, things will become straightforward. Convert 2 raised to negative 40 to 754 standard. What is this number going to be? Denormalized, right? So this has to be a denormal, right? So because it's smaller than 10 to the negative 38. So if I want to do this, you see, no, even here. What are the things that I need to figure out here? This can be easily figured out, right? This is the sign, no problem for the sign. This is fixed, right? The only thing that I need to figure out is the significand, or in this case, significand is equal to the fraction. This is the only thing that I need to figure out, yeah? So if I'm given the value of the number, which is, x equals that, right? If I'm given the value of this number, 2 times 10 to the 40 is what I'm given. And if I'm after this, what should I do? I'm given this, right? I'm given this as what? 2 times 10 to the negative 40. Yeah? That's the example that we are working on. This is a fixed value. I want this. Well, can I say this? Significant is going to equal 2 times 10 to the 40, negative 40 divided by 2 raised to negative 126, right? Just divide it. I'm treating sign differently. Just divide it, right? Okay, so if I divide this, I get 0.017, and you guys can check this. 0.017 is the significant in decimal. I would need to convert it into 23 bits, right? You guys know how to convert a decimal number to a binary number. What do? You keep multiplying it by 2, record the integers, right? Multiply by 2, record integer, multiply by 2, record integer, and so on. You'll have to evaluate 23 bits of that. Once you do that, that's how you get this. So I'm going to write that again. So you are getting those by 2 raised to 2 times 10 raised to negative 40 divided by 2 raised to negative 126 gave you 0.017. This is in decimal. When you convert it into binary, you will get all of these. In other words, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12, 13, 15, 16, 17, 18, 19, 20, 21, and 23. If you did all of that, you would get 0.017. And the way to do that systematically is what? Keep multiplying by 2 and record the integer part of the result. And then you throw away the integer part, move on to the next multiplication by 2. So that would be your denormalized representation. Positive exponent field has to be a 0. That's how we are identifying that it is a denormal. And then followed by all the fraction bits, all of these guys over here. So there is a way for you to identify it in the binary sequence, and there is a way for you to identify it in denormal in the integer, right? The number. Number has to be less than 10 to the negative 38 or less than 2 raised to negative 126. In the bits, you see exponent field all zeros, you see the fraction field non-zero, you know it's a denormal. So when you identify that to be a denormal, you just have to adjust a few things. What significant field is going to equal fraction field, and the exponent field is going to be in the XS 126 format, not in the XS 127 format. Questions? This is looking very simple. Yeah. Yeah. There are websites for you to do this. All right, but here on the exams you will be asked to convert by hand. So get some practice. You can use the online calculators to as a check. All right, infinities and not numbers. How do you identify that? For infinities, your exponent has to be all ones, and your fraction field has to be all zeros. So if exponent is all ones and fraction field is all zeros, that's an identifier of infinity. And depending on the sign, it can be plus or minus infinity. It can be used in subsequent calculations. It's not that if you get an infinity, your arithmetic stops. You can keep using that in the subsequent calculations after that, avoiding a need for you to check for overflow. Another thing that can happen, exponent field is all ones and fraction field is non-zero. So you see, you are looking at all the combinations of exponent field, all zeros, fraction, all zeros or non-zero. You get two combinations. Exponent field, all ones, fraction field, all zeros, non-zero. Two possibilities. So if exponent field is all 8 ones and fraction field is non-zero, then that's an indication of not a number. When does this happen? You divide by 0. That's when it happens. Indicates some undefined result, like 0 divided by 0 result. This again can be used in subsequent calculations. So the programmer has to worry about it. On top of this, the programmer has to do the check for any of these exceptions. Arithmetic in floating point. How do you deal with arithmetic in floating point? This is going to be very sort of intuitive. When you want to add two numbers or subtract two numbers, what do? Say you have something like 1.6 times 10 to the 9 plus 2.1 times 10 to the 10. What do you do then? Well, you can equalize the exponents, which means you can increase this guy to a 10, or you can decrease this guy to a 9, equalize the exponents first. So you can say, all right, if I wanted to increase this guy, what can I do? 0.16 times 10 to the 10, right? Plus 2.1 times 10 to the 10. Equalized exponents. Then you add the significance. So add this number to that number. What do you get? 2.26 times 10 to the 10. Then, depending on how many bits you have, round off the significand of the sum. And you maybe also used associativity. So for example, if you have a plus b plus c, a plus b, then you can do c, and so on, for addition as well as for subtraction. So the key over here is to equalize the exponents. Now, another thing that you have to be careful about is you equalize the exponents, you do the addition or subtraction. At the end, you will eventually need to express it in the 32-bit format, right? So if you want to express it in 32-bit format, again, you will have to do the normalization. Depending on if it's a normal or denormal, again, you'll have to figure out that exponent. You'll have to adjust that exponent in order to go for a normalized representation. For multiplication or division, over here you adjust for bias. So equalize the exponents, add them, 10 raised to 9 multiplied by 10 raised to 10. You add the exponents, multiply or divide the significants, and then before you represent that, you normalize it. And then you can also round the significant of the product depending on the number of bits you have in the significant field. For arithmetic in floating, let me finish this table here. We were talking about normals. We did a detailed discussion on normals. Over here, there's a range of the exponent field. Starts at 1, ends at 254. And any bit pattern over here goes in the fraction field. Could be positive, could be negative. How do you identify 0? Exponent field has to be 0, fraction field has to be 0. 8 bits 0, 23 bits 0, that's your 0. Denormals, exponent field has to be 0, fraction field has to be non-zero. That means any one bit has to be a 1. Infinity, exponent field has to be all ones, fraction field has to be all zeros. Not a number, exponent field has to be all ones. Any non-zero pattern for the fraction field gives you a not a number. Wait, I thought there was. Right, let me talk about this first. For floating point instructions in MIPS, they are slightly different instructions. All the instructions that we are looking at, they were all integer based. The floating point instructions are different. For MIPS, you have add .s. .s or .d corresponding to single precision or double precision floating point instructions. So add, multiply, divide, all of them .s, that's your single precision instructions. And then you have their corresponding double precision instructions as well for adding, multiplying, and so on. What are the registers being used? Well, there are 32 floating point registers starting at F0, ending at F31. So 32 floating point registers that are reserved for floating point instructions. That would be 32-bit registers, right? But what if I want to do double precision format arithmetic? Well, if you want to do a double precision format arithmetic, you combine F0 and F1 for the one double precision number. So you will get what? 16 double precision format registers. You're combining them in groups of 2s. You will have 16 of them. So those are the registers that we use for floating point, and the instructions are also adjusted with a .s or a .d depending on single precision or double precision instruction. Now coming to the double precision in floating point, which is what? The IEEE 754 64-bit double precision format. What changes? Sign bit doesn't change. You still have one sign bit. Exponent bit field has changed to 11. You guys might be concerned a bit. Exponent field has gone from 8 to 11. Exponent field controls what? The range of the numbers that you represent. So it might be concerning, right? We doubled the number of bits. So is the improvement on the number of the range, is it good or bad, right? Did we do a bad job? To answer that, let me answer it with the range of the resulting numbers. The range with 11 bits in the exponent is actually 2 times 10 to the negative 308 to 2 times 10 to the 308. So it's a pretty big range already. I don't need to have more bits for the exponent, which is why we stop at 11. And the rest of the 52 bits to round off the 64-bit double precision format go in the fraction field. So you've got the 1, you've got 11 bits for exponent, followed by 52 bits for the fraction field. So with the fraction field, you have got a pretty huge improvement, right? So significant has got 29 more bits, which means our precision has got a very, very big improvement. But our range is pretty decent as well. Again, you will have the same thing, zeros. It's going to be in the XS 1023 format, right? So you guys have seen all of these things. We talked about this. All right, excellent. I'm going to stop over here. You guys will not do activity 8. You guys will do activity 7 now. All right. So guys do activity 7. Next class, we are going to get into data path. MIPS data path is going to be interesting. It's going to be a lot of diagrams. It is going to be so it's going to be an important discussion. Just leave it at that, because the 5-6 lectures following that are going to depend on how well you understand the material in the next class. We have exam 1 coming up Thursday of next week. So you have a week and a half or so left for exam 1. I'm going to start posting material on the Class Piazza webpage for some back exams, some topics, logistics, and all of that. Right now, my expectation is going to be that almost all of you guys are going to be available during the class time for the exam to be conducted at 8 to 10. But if you are not, it's a really good time for students in China, where of all our international folks, that are not able to make it to in-person classes are over there. So it's a good time for them because it's 8 p.m. over there. It's not too late. And you guys who are on campus, just got to get some coffee, keep it ready, and then wake up. If you train yourself for a few days, 8 a.m. is not too bad. So you guys can do that. But if you have any sort of emergency situation, some serious reasons why you cannot take the exam between 8 to 10, you got to let me know right now. This also applies to people who are listening after class, maybe tomorrow, maybe day after. So you guys need to let me know. Questions? Go ahead. I have no idea. That's an interesting question. No idea. 1985. So it's not even the year that is. Maybe they were going in the list. 751, 752, 753. Okay, 754. I'm not sure. I don't know it. Googling required. All right, let me stop recording here.